more than
You can skip probably 30 seconds.
And I didn't even leave on.
There's other, I can't. I keep sitting there. I don't watch it. I literally go to more.
Mine's full of, okay, mine's full of AI stuff. Like weird AI stuff and Minecraft stuff. Because I found this
Always
one.
receiving Minecraft.
Well, okay, but I really like this.
Would the code red just taste like disappointment now? Is that why you have to go to Dr. Pepper?
Well, I'm out of code red here.
So the doctor ordered. So you're all good? Dr. Pepper.
Well,
And remember, there's not
Here's some sweet ones.
remember, there's not a period after the doctor, so it's not actually a previous thing. It's a drip.
You can skip another 30 seconds. Probably.
No, I remember that from Dr.
I think so, yeah. Like I just like
It's like you bring like
what was the what was the
Dr. Pepper.
I told you. I do remember that ad for Dr.
Well, I didn't hear that.
Lots of highlights. We missed the same number on the
Pretty much.
I don't know. Like all of a sudden we decided to start singing during game diverse for no apparent reason. Okay. Time to
It doesn't matter.
die or something. I don't know.
Well, I just did it backwards,
Yeah.
but the signs,
You're deep
the
in
signs
the
stay the
water.
same. Signs are
Why?
I hope you get it.
I hope I don't. I don't need to fix it, it's still.
Hey, you should send us the problem. No, because we also did it for Cohen. I sent it to some of the base house kids, and they all voted for Cohen. Cohen didn't get it, obviously, because he didn't have attention. So
Right, because that's.
You're looking at problem 13.
We're looking at number 13.
Who called it? Who called it? I know, it's crazy.
13.
I told him good luck with the gap. I didn't put three, so.
Okay.
This. What'd you guys do on
Yeah.
One.
Nobody's even waiting in the text.
That's really it.
I thought it was like difference in percentage. That's like all six. I don't know.
Why?
See, that's one of the I thought it was actually about, I thought it was actually about.
I don't know.
Because it makes no
I
sense.
think.
Oh.
what does
What we
that?
don't know is if.
I don't understand.
Yeah, isn't it?
I want to talk to the whole
What? Wire.
What? In the current
No,
though.
he's
Through the current.
I mean, like, I'm.
Cohen, how old is that assignment?
I said.
Assignment was like 3 days ago when it came in.
Oh, no.
Yeah,
He let it marinate before he
Okay, so let's talk about number 12 and 13. Okay, because they're related, but yet they're not. So, when you look on number 12, and I can't remember what we talked about this morning, but I think I might have to revise after looking at this picture. So, on number 12, they're the same battery. So what's important here is if you look at Ver, okay? So, on both of these, you have the exact same battery. That's cool, right? Nice. Don't worry about 13, we'll get to 13 later. A completely different beast. Danny, or have you started the camera? We're good. Okay. So, the significance of why they give you that L is because resistance equals rho L over A. So, on number 12, both of the wires have the same resistivity value because everything's the same, the area is the same. So, the significance in terms of the difference on number 12 is the fact that on that second one, you have a longer length, okay? So with a longer length, what's going to happen to the overall resistance within the wire?
Increase.
it's going to increase, okay? So if voltage is staying the same, because it's the same battery, and your resistance increases, then to make everything balance out, what has to happen to your current?
Has to decrease.
It has to decrease. So that one that has the longer length, because of the fact that there's more wire for that to go through, that's going to have more resistance, it's going to have less current. Now, one of the misconceptions that happens a lot with electricity is that if you look at the movement of, and this is the conventional idea of the current moving from positive to negative, thank you, Ben Franklin, is that one common misconception is that you think, like on this one, you would say that 1 would have more current than 2 is, because of the fact that it's leaving the positive terminal and it's going around, and so 1, because it's closer to the source, is going to have more current, as Jacob emphatically shakes his head no, okay? So that is a misconception. Within the wire itself, as long as there's no deviations, they're not branching off, whatever, these are going to be the same within the wire. So in number 12, these currents are going to be the same, but the one with the longer wire has more resistance, so it's going to have less current. Okay? Go with that one. Now, let's talk about number 13. So this boils down to, and literally, when I was teaching in the Peace Corps, this is how I developed this story. Because most of the kids, like, lived in, it's almost like a communal thing, where you would have multi-generational families that all lived kind of in the same compound, which wasn't any big deal because, hey, you want a new house, you go get some mud, some straw, some cow manure, you spend the day, you build the walls out of mud, and then you get down and you go cut some tall grass, and you put some grass on the roof, and boom, you have a house, okay? So it wasn't like, oh, we have to get a building permit and everything. It's like, go get some dirt, some straw, we'll build a house. So everybody, it was cool. So it was a generational thing. Like you literally grew up in the same compound as your grandparents and some of your aunts and uncles. So everybody knew the story of the family. And so there's 2 ways that your mom could cook. Your mom could cook in series, or your mom could cook in parallel. Both have their advantages. So in this situation, imagine this is the kitchen. Okay, so this is people coming in needing food, all right? So imagine that you're going to block off like this half of it, okay? That's not there, don't even worry about it. So if you're only talking about this half over here, this would be like you're an only child. So Cohen isn't, unless he's not, but let's just say. Okay?
My parents love me?
I know. And you get all of the food.
This is the best hypothetical ever.
It is. Okay. That's so pathetic. So, Cohen is loved. All right. So anyway, so this is just Cohen. Okay, he's an only child. He gets all of the food. So he leaves every morning. Mom gives him his lunch pail, kiss on the forehead, writes him a note. Love you, you're special. Boom, Cohen goes. He fights the good fight of education, annoys Mr. Burkamp. He comes back home. He's tired. Mom says, hey, let me give you another lunch pail. And the current throughout that entire thing is going to stay the same. No, Cohen isn't the only child. Cohen has a little brother, who's I hear is even more annoying, but let's go with that. Now, Cohen's mom cooks in parallel, okay? So what that means is that she's going to give Cohen and his little brother the same amount of food as they leave. So this is the 2 of them, imagine this is the 2 of them together walking towards the car, okay? So together, because they're together at that point, they've got all of that food right there. Now, after they split, Cohen still has the same amount of food that he did before. Teague has the same amount of food over there. So at that point where they're walking together, what do you know about the current? It's greater because of the fact that this is the current before it gets split, okay, because they're in parallel. So this is, they're walking out the front door. Mom says, bye boys, have a good day, storming the castle. They leave, they go storm the castle. Okay, does anybody know the movie that I'm referencing?
Yes.
No.
Princess Bride, come on, Jay.
There you go, Princess Bride. So they go storm the castle, they come back. There is a castle involved in the Holy Grail, don't get me wrong, which is also fun. Okay, I think my nose in your general direction. So they come back, they're walking back into the kitchen together, they've rejoined. They go through the kitchen, they get food, they leave again. So on this one, the maximum food is going to be right there when they're together. Okay? Does that make sense? Now, what you also see once we begin to study resistance, and this is true, if your mom cooks in parallel, your resistance goes down. So mainly because of the fact that everybody's getting the full amount of food. It's like, oh, everybody likes that. It's like, oh, right, yeah, mom cooks in parallel, right? Everybody gets the same amount of food. Everybody's happy, and the resistance drops. But unfortunately, what's going to happen to the amount of food in the kitchen?
It's gonna decrease.
Yeah, it's going to decrease rapidly because she's giving everybody the same amount of food as you normally would. So that's the downside, is that, okay, hey, great, there's less resistance, but you're going to run out of food fast. So there's your downside. Okay, now here's the other way that, let's say you're going, man, I don't know what to think about this. So here's the story. Look at your house, okay? Is your house wired in parallel, or is your house wired in series? Parallel. Wired in parallel, right? So this is a situation where it's in parallel. So it isn't like you turn on one light and then you walk through the house and you get in your bedroom and you turn on another light. When you turn on that second light, the first light doesn't get dimmer. It isn't like you take the same amount of electricity and split it between the two lights, okay? And then, oh, you turn on the TV. Oh, there's another draw of electricity. And then the lights, the more you turn on, the lights just get dimmer and dimmer and dimmer, okay? Which would be bad.
We had a waffle maker that did that.
Would what, make waffles?
No, it would dim the lights in the whole house when we plugged it in.
Really?
Yeah, I'm pretty sure it took more energy than our oven did. They made the best waffles, but it eventually like melted. Like the insulated cord and the outlet was plugged into, just kind of like.
Oh, I wonder why.
This is a sketchy waffle.
Okay.
30 seconds.
Oh. Anyway, now on question number 10. Okay, so let's talk about question number 10. So you change the temperature of a segment of metal wire, the dimensions change, the resistivity changes. How does each of these affect the resistance of the wire? Okay? Now, when you look at this in terms of dimensions, so on number 10, when you heat up a wire, what happens to the length?
When you heat up a wire,
When you heat up any metal.
expands.
It's gonna get longer.
So you're going to increase the length. So based upon a value of resistance, when the wire gets warmed up, the length gets a little bigger, which would increase the resistance. Okay? But what happens to the cross-sectional area? Cross-sectional area gets bigger as well, right? Because it expands in all dimensions. So your increase in length increases the resistance, but your increase in cross-sectional area decreases it. So based upon pure, this is leaving the value of the resistivity out of this thing. just in terms of the dimensions, they're kind of conflicting ideas. Raising the temperature makes the length bigger, but it increases the cross-sectional area. So that's about a wash. Where you run into trouble is the value of rho, which is that resistivity. That is very temperature dependent. So as that temperature rises, your resistivity increases. So this is why, like, solar panels are more efficient in the winter than they are in the summer, because of the fact that there's less resistance within the wires within the system, because it's a little bit colder. You don't see a huge difference. So your resistivity is temperature dependent. And you can make the analogy that, let's say it's really, really cold and you're trying to navigate through people and you're trying to walk. Well, if it's really, really cold, people just tend to stand there and shiver and they don't bounce around very much. Oh, okay, it's easy to walk through. If it's 80 degrees and they're more active, then that increases the resistance as you try and navigate between the people because they're vibrating more. So on an atomic level, that same idea plays out. As the particles vibrate more and more, it's harder for the electrons in the electric field to get transmitted through because there's just more collisions and your resistance goes up. So there's that. On number 18, if you multiply your answers to B and C, you should get your answer to A. Okay? A little bit weird. On number 20, that value is going to be very, 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 very much less than 1, like 0.0 something. Yeah. So if you look at what's happening on, this is what I tried to show you all yesterday, is that if you look on 20, what's going to happen to resistance if it is stretched to twice its original length without changing the volume of the wire? So this is why I came up with that equation yesterday. So if you look at resistance equaling rho L over A, which you can write it as rho L volume over length, and that becomes rho L squared over volume. So if you look at this in terms of like a ratio, so because of the fact that the volume is going to stay the same, that's going to drop out, and then you look at this as being, oh, that's going to be L squared. When you get to question number 21, and this is with corn plants, and you tend to sit there and go, well, this is just horrible because of the fact that you're missing like one of the dimensions. So here's the little trick that you can do on 21, is if you start with the idea that you have rho L over A, which is your resistance. So if you solve for resistivity, you get resistance A divided by L. Okay? And then you can say, oh, that's resistance times volume, not volume squared, over, that just turned into a debacle.
This much I need we scale the print now, so this one page.
Anyway, so you do a little bit of voodoo on 21 in terms of that substitution for volume. And if you look at volume being length times width times height, then you can actually cancel out one of your L's, and or you can just make up numbers and put that in. Both of your answers on 22 should be, this is a huge-ish. The first answer should be around like 9 times 10 to the minus second. And that answer to 22B should also involve a 9, but it's like 10 to the minus third. Okay? So 22 is 10 to the minus second. 22B is 10 to the minus third. Your answer to 30 should be around 50.
Around?
What's the difference?
Take around however you'd like. Make sure on 29 you should have a graph where you have current here and voltage here, and you should have two different lines. Make sure I know which one is which. Okay? Make sure I know which one is which. All right. Anything else?
31. Yes, 31.
Okay. Wow.
Sorry, my bad. Didn't mean to yell that at you.
Yes. A little aggressive. The whole thing?
Yeah.
Right,
Why
start to
not?
finish?
Why not?
Just the entire in detail.
Wow, you're asking for a lot.
Can I say they're pretty needy?
I was just
No,
gonna
I'm
say.
so actually, I know.
Yeah.
I know it's
The difference in area. Which one is it? I don't know why. Because, yeah, the answer is. Because, well, half of my
But I was like,
Okay,
because I used to.
so let's start with this. So potential difference, and remember, potential difference does not mean potential energy. Potential difference is a measure of what? Voltage. If you wanted potential energy, that would be measured in joules.
That's on me. That's on me.
Okay,
I was testing you. I was testing
so you've got the potential 120 volts, and that's what standard household systems are built off of. Households are run off 120 volts, okay? And then you've got the length to be 0.6 meters, so all you have to do on A is just use voltage equals Ed, okay? That's all you have to do. Then, on B, it's gonna be, suppose the length were doubled without changing the diameter, what would the electric field strength be in this case? So, you're still hooked up to 120 volts. So, the voltage is still 120, but now you're gonna double the length, so what's gonna happen to the value of your electric field? Connor asks.
Alright, can you ask the question again?
I still have the 120 volts.
Yes.
I'm going to double the length.
Uh-huh.
Same voltage. I double the length.
Yeah. What was the
What's going to
question?
happen
Yeah.
to the electric field?
Oh, it's gonna have.
There you go.
I didn't know what you asked. I didn't know what the question was, okay? Wasn't ready for that.
Now, C is simple. All you have to do
It's simple, he says, Charles.
is ver it up.
You didn't. Struggle.
Meters.
Okay,
Yeah,
cool with that one?
yeah. I was just confused of the order of the questions, I guess.
A, B, C, or D was confusing?
No, I don't know why they asked question C ahead of question D, because it felt like they should ask question D ahead of question C.
You could have done it ahead of it.
I know, I
then
did.
just gone back.
I did.
Okay.
I got the right answers, I think.
Okay.
I mean, I guess we'll see when I get this back.
Your answer to 31D should be around 500.
Yeah, it's around
Yeah.
within a couple. Ish.
Ish.
Around a couple.
It's an ish. Okay.
Tens.
After that ish,
Can do a couple off.
anything else? Pretty straightforward, go once, go twice, so.
You signed for who signs for them?
Yeah, I said, for maybe for what? Check what I tried to make.
Hey,
It's gotta be good, really scary.
I'm rather pissed off.
Also wise.
Because it's probably not that it seems stupid that I didn't catch that.
You will help me.
Oh, I know, it's just like,
Where it's split off into two
What?
sections.
if you do something weird. Well, it weighs to.
He knows a way to shave off some of that weight.
Like, you know, when you go slicing through and maybe bounce around. No. Yeah, it would be a hamster.
Fight, and it was about
1.5.
You mean rope?
Either way, I don't know what he's talking. It is P. P is power. What's up into my feet? Is that power? Way more than it should. Talking about power here? I got the power.
Okay. So, today we're going to introduce a new equation, and it's one that has like a lot of applications and a lot of variations on the theme. So we're kind of working like one big circle to figure out how this plays out. So first off, we got to go old school discussions about power, okay? Old school. So what's the simplest way to calculate power? It's something divided by something. Work divided by time. Okay? And that work is going to be measured in
Watts?
joules.
Oh, wait, sorry, work, sorry. Isn't that power in watts?
Yeah, power joules, yes.
Sorry, you said work and my brain was trying to.
Which is also joules per second, right? Okay? Which is the same as watts. Now, this is where it becomes relative to light bulbs, okay? Because light bulbs are measured in watts, which is joules per second. So if you have a 100 watt bulb, that means it's consuming 100 joules per second, or producing 100 joules. So what's brighter, 50 watt bulb or 100 watt bulb? 100 watt bulb is, mainly because of the fact that there's more energy per unit of time, okay? Now, so we're going to do a little bit of voodoo, not much, just a little bit. So you can also look at power as change in energy per unit of time, okay? Which is the same thing as work, okay? So it's a very multi-dimensional thing. Any type of energy change is going to require work. Now, so here's the substitution to show you where this equation comes from. So if you look at a change in UI is charge times your voltage, okay? Which makes sense because of the fact that if you look at that, volts is measured in what units? Joules per coulomb. And then if I multiply that by charge, which is in coulombs cancel out, I get joules per second, right? So, if I rewrite this just a little bit differently, and I isolate charge per unit of time, well, charge per unit of time is equal to what? So that's coulombs per second, which is amps. So that's going to be I times your voltage. So when you look at the idea that pivot up, okay, so you vert it up or you pivot up. So power then, if you look at the units, you've got I, which is coulombs per second. You got volts, which is joules per coulomb. The coulombs cancel out. You get joules per second, which is watts. Okay? Now, what's on your equation sheet is this. So here are the two that are actually on your equation sheet. You got PIV, and you got I equals delta V over R. So typically in households in America, which is where we're at, so typical voltages remain the constant at 120. So let's say, for example, you have, was it waffle iron?
Yeah.
Okay? And if you look at the power consumption, and if you look on the back of a lot of your, like a blow dryer, curling iron, something like that, it'll say it's rated at so many amps. Okay? So let's say that that's rated at 15 amps. So if that's rated at 15 amps and you plug it into your household outlet, and that's 120 volts, you can figure out the power required to run that. Now, here's what's going to be important. Somebody take 15 times 120.
1,800.
1,800 watts, right? Now, that's 1,800 joules per second. So if you run that for, say, 30 minutes, then if you multiply that by time, say 30 seconds, what do you get?
54,000 joules.
54,000 joules. So obviously the longer you run an appliance and the more amps it draws, the more electricity you're going to use. So this is why if your parents say, hey, you're leaving the room, shut out the lights. Okay? Well, you leave the lights on and nobody's in the room, and this becomes relevant. It's like, oh my God, I'm becoming my parents. Well, if you look at leaving a light on and there's nobody in the room, really, what's the point? Okay? Because of this equation right here in terms of PIV, the 120 volts is going to be the same. So if you shut off the light, guess what? What becomes the current going through the bulb?
Nothing.
Zero. How much power do you use? Nothing. Okay? That's why if your parents hark on you, it's like, hey, turn out the lights when you leave. That's why. Because the more power that you consume, guess what? The more it shows up on your electricity bill. So when you all become heads of households, okay, or even if you're just living on your own, it's like, oh yeah, I need to turn out that light. Because it's literally like, why waste the money paying Evergy because you leave a light bulb on? Okay? Just doesn't make much sense. All right, now, you need to get fluent in these different equations. So here you've got PIV, okay, so that's the basic one. And then you also know that you can also vert it up. So this is your basic equation. Power equals current times your voltage. But voltage also equals I times R, your current times your resistance. So could I substitute IR in for V?
Yeah.
Absolutely. So power can also equal I squared times R. Cool with that. Now, here's how this would play out. And this will be important once we begin to study like what happens with bulbs. So if you look at, and this is where it goes back to your mom, whether she cooks in parallel or if she cooks in series, okay? So if you go back to that idea of, with that initial story with the batteries, well, if your mom cooks in parallel, then if you look at this in terms of that current, if she cooks in parallel and you get more current in the system coming out, what's that going to do to the power calculation? It's going to go up, okay? And if you look at power being like food calories per second that are going to go out in the kitchen, so if your mom does cook in parallel, then that I is going to go up, and then you look at the resistance. Now, typically, whether it's a bulb, resistor, whatever, the resistance of a particular element is a fixed value. Well, once we get into a deeper thought process with circuits, and you combine them in series or parallel, you can change the overall resistance of a circuit, but you can't change the individual values of what's going to happen in that resistor. Okay, so equation number 1, you pivot up. Situation number 2, you can write it as I squared R. Now, voltage also equals what? Or excuse me, current. Current also equals what? Well, in terms of Ver, current would equal V over R. So if you look at PIV and I equals V over R, you could take that and substitute that in there. Oh, okay. So power equals voltage squared over R. Now, this is the one that gets a little bit counterintuitive, okay? Because with this one, and this, it works beautifully mathematically, but I'm going to tell you right now, this is a little counterintuitive. But it boils down to what you hold constant and what changes. If your voltage or your potential stays the same, say it's at 120, whatever that is, as you increase the resistance, okay, what's going to happen to the power?
It's going to decrease.
It's going to decrease. That gets a little bit wonky counterintuitively. You would think if you increase the resistance, that would need more power. Okay? So just intuitively you would think, oh, resistance goes up. Well, here's the other part of the story. Like, we'll spend more time talking about this since we get into light bulbs. So if you look at that in terms of here, if your resistance goes up and your voltage stays the same, this is where it kind of goes in a different direction. So, go away. So, if your voltage is constant and you increase your resistance, what's going to happen to the current? It's going to decrease. So, that one, then if you plug that back into PIV, that one makes sense. Oh, I increase my resistance. With the voltage stays the same, I have less current. Less current with the same voltage would require less power. With this one then, it's the same idea. So this is why if you increase that resistance here, that power goes down. So in one situation it kind of makes sense intuitively, the other one is kind of counterintuitive. But mathematically it still works as a nice model. Okay, so here's how this would play out. So let's say that you've got I don't know, a 75-watt bulb. Typical, okay? And in a standard household situation, you have 120 volts, okay? For whatever reason, we picked 120. So what can I do with a 75-watt bulb and 120 volts? What's one thing that I could find? I could find current. Oh, okay. So I could pivot up, right? And I could go, okay, I can take the 75 watts and divide that by the 120 volts, and you get what? 0.75 amps, okay? Now, what would happen to that current if the power goes up? If the power gets bigger, what's going to happen to the current? Charles?
75 divided by 120?
Yeah.
0.75.
0.625.
It's like you all are looking, okay, 0.625?
Yeah, so 0.63.
Yeah, let's go with 0.625.
Do like 5 multiples of 5.
Okay? Back to our story. If you jump it up to a 150, what's going to happen to your current?
No, it's gonna increase.
If you jump it up to 150, right? That's going to require more current. Okay? Makes sense. Now that I know the amperage, could I find the value of the resistance? Sounds like a Star Wars theme. So, how can I find the resistance? Well, if you look at Ver, at this point, what do I know? Got the voltage, that's 120. I got my amps, which is 0.625. And then I can find my resistance that way. So somebody take 120 and divide it by 0.625.
192.
What'd you get?
192.
192 ohms. Okay? Cool with that. Not a big deal. Now, this is where it gets tricky with bulbs. Okay? So I gotta do some writing because I've got to lay out two different scenarios here. So give me a second. So if you want to stand up, take a stretch. I need to do some writing. Because I want to get it all written out before I start to
Remember that?
Do you remember that set of fuzzies at basketball games?
I can do the same thing, honestly. I thought the same thing. Yeah, weird. Everything kind of hurts. I got something that's not putting it out a little bit. Why are you putting it in your name?
Joe, we're so sad you're hurting. Did you get this? Oh, I was just having a thought. I was like, this kid should
Last meeting tomorrow.
Yeah. Do you guys get there?
Yeah, it is. Your feet. Yeah, it is. And I look at my feet, I'm like, what am I doing? So I'm like,
Yeah, because I did this one.
no, you should. Charlie, you don't want it. You know about your feet.
It wasn't mine. I put on it too bad.
I think I said I'm waiting for you.
Oh, it's in your anchor.
my first thing.
I know.
Oh, I don't.
I mean, have you seen the type of people who
I want to.
Have you seen that side of the
I'm not, but.
Oh, yeah, that side of the.
They're little boys.
That's crazy.
Have you heard Evan Hall?
Fancy right there.
Yeah, you heard it. I can actually. It's like that. I can't replicate the laugh. It's like you hear it.
Hey, I've heard Deacon can give a really good Evan impersonation.
We're talking about.
Eagle laugh, eagle laugh.
Start choking on
The weeklies shit out. I'm on the mall again today. I've done that for the past. I might be one of those people when they I was doing okay. I couldn't grasp it real well. And then the day we got into weird stuff. I was thinking he can't see what it was stuff like. Right?
What was Checo doing? That was good.
And it took art for something.
They don't lose the player.
Can too, but
But I see it happen first.
But, you know, we live and we learn, I guess.
Only way to
Dude, stop.
Have you taken calc?
Have you taken calc? I took pre-calc.
And stats. Hey, buddy, you're talking about you're talking about girls.
Are you first? Actually, are you touching me? You're the problem. You're the reason I'm like 3.1%. Freak you. So
No, I thought it was top 11.
It's like, wait, what's the class? What's the class?
No, it's not. Yes, it is. The class number dropped and I'm not in it anymore because of it. It's so dumb. There's no way we dropped 50.
No way.
Okay. There's no way. Third lucky teachers, why so mad? You should not be giving this.
Okay.